Space has always captured humanity's collective imagination among the pantheon of celestial bodies that have fascinated us. Jupiter stands out as the largest planet in our solar system, with its vibrant stripes and prominent great red spot making it easily recognizable. But there's far more to Jupiter than its size and famous storm, and our knowledge has grown exponentially with advancements in space technology and exploration. Jupiter is a gas giant consisting mostly of hydrogen and helium. Its diameter is approximately 11 times that of Earth, and it's so large that over 1,300 Earths could fit inside it. Despite its size, Jupiter has the shortest day of all the planets, rotating on its axis every 9.9 hours. Jupiter's magnetic field is the strongest of any planet in the solar system, created by electrical currents driven by its fast rotation and the movement of metallic hydrogen within its outer core. Jupiter's famous bands are actually high-pressure zones characterized by lighter-colored clouds, while its darker regions are low-pressure zones. The vibrant colors we see are due to different types of clouds. Ammonia crystals create the white bands, while other chemicals produce reddish, brownish, and yellowish hues. As for the Great Red Spot, this iconic feature is a persistent high-pressure region in the atmosphere, resulting in a storm that has been ongoing for at least 300 years. The Great Red Spot is one of the most recognizable features of Jupiter, the largest planet in our solar system. At its widest point, it stretches 1.3 times the diameter of Earth, although its size varies over time. Notably, it has been shrinking in recent decades. The storm has been continuously observed since the late 19th century, but historical records suggest its existence for at least 300 years. The Great Red Spot is located in Jupiter's southern hemisphere, nestled within a westward moving jet stream called the South Equatorial Belt. The red color of the Great Red Spot is still a subject of research, and it is thought that the color may come from complex organic molecules, red phosphorus, or possibly compounds containing sulfur. The exact chemical reactions that give the spot its vivid color remain a mystery. The storm rotates counterclockwise with a period of about 6 days. Interestingly, the rotation speed, size, and color of the spot can change, reflecting the storm's complex interaction with its surroundings. The longevity of the Great Red Spot is intriguing. While storms on Earth last for days or weeks at most, the Great Red Spot has persisted for centuries. This longevity is likely due to Jupiter's rapid rotation and lack of a solid surface, which minimizes frictional dissipation of the storm's energy. The Great Red Spot is a window into the atmospheric dynamics of Jupiter, a gas giant with conditions vastly different from our home planet. Understanding this celestial maelstrom not only unravels the secrets of Jupiter but also sheds light on the broader principles governing atmospheres, including our own. Jupiter has 4 largest moons, Io, Europa, Ganymede, and Callisto, known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. Each of these moons is a world unto itself. Io is the most volcanically active body in the solar system, with its surface covered in sulfur and sulfur dioxide, giving it a colorful, mottled appearance. Europa has a crust of ice, and scientists believe it might harbor a subsurface ocean, making it a potential site for extraterrestrial life. Ganymede, the largest moon in the solar system, is the only moon known to have its own magnetic field. Callisto, characterized by an extremely cratered surface, is believed to have an ocean beneath its surface as well. Jupiter was known to have 79 moons, but additional moons may have been discovered since then. Saturn isn't the only planet with a ring system, although much fainter and smaller. Jupiter also has rings composed mainly of dust particles from impacts on the planet's small innermost moons. These rings were first discovered by NASA's Voyager 1 spacecraft in 1979. The study of Jupiter has come a long way since Galileo's first observations. Multiple missions, such as Pioneer 10 and 11, Voyager 1 and 2, Galileo, Juno, and more, have been sent to Jupiter to study its composition, magnetic field, and moons. Pioneer 10 and 11 were the first spacecraft to make a close approach to Jupiter, providing valuable data about its radiation belts, magnetic field, and some moons. Voyager 1 and 2 made significant discoveries such as detecting Jupiter's rings and confirming Io's volcanic activity. The Galileo orbiter spent 8 years studying the planet and its moons, and the attached probe made a direct plunge into Jupiter's atmosphere, providing the first still ongoing as of 2021, has made significant contributions to our understanding of Jupiter's internal structure, atmosphere, and magnetosphere. Jupiter, the colossal gas giant, remains a focal point of curiosity for astronomers and space enthusiasts alike. Its impressive size, complex atmospheric dynamics, multitude of moons, and faint ring system make it a fascinating object of study. As we continue to explore Jupiter through telescopic observations and space missions, we unravel the secrets it holds, enriching our understanding of the cosmos. For now, we marvel at the celestial symphony Jupiter conducts, its presence a testament to the intricate, diverse, and vast nature of our solar system. Moving on to Venus, it is nearly identical to Earth in size, making it one of our most similar neighbors in the solar system. With a mean radius of about 3,760 miles or 6,520 kilometers, it's approximately 95% the size of Earth. Its mass is about 81.5% that of Earth. This similarity in mass and size means that Venus also has a comparable density to Earth, approximately 5.24 grams per cubic centimeter, implying a similar rock-iron composition. Venus and Earth have a comparable structure, with a central iron core surrounded by a rocky mantle and a thin crust. The core of Venus, while not as well understood as that of Earth, is believed to be partially liquid, similar to Earth's. This iron core is estimated to be about 2,000 miles or 3,200 kilometers in diameter. Above the core lies Venus's mantle, composed of silicate rock that extends up to approximately 1,550 miles from the planet's center. This is overlaid by a thin crust estimated to be 6 to 12 miles thick. The rotation of Venus is a unique characteristic on the planets of our solar system. Unlike most other planets which spin on their axis in the same direction that they orbit the Sun, Venus rotates in the opposite direction. This phenomenon isn't yet fully understood by scientists, but some believe it may be due to a massive collision with a celestial body in the past, which altered the planet's rotational dynamics. Venus rotates extremely slowly with a solar day, a full rotation on its axis, taking 243 Earth days, the slowest rotation of any planet in the solar system. This slow rotation contributes to the planet's lack of a significant magnetic field. Another quirk of Venus rotation is that a solar day on Venus, the time from one sunrise to the next, is shorter than its sidereal day due to its retrograde rotation. Rotation and orbit around the Sun. The solar day on Venus is about 11 Earth days and 16.75 Earth hours. The planet's year, the time it takes to orbit the Sun, is about 225 Earth days, which is shorter than its sidereal day. This makes Venus one of the few planets where a day is longer than a year. The surface gravity on Venus is about 90% of the surface gravity on Earth. This means that if you were able to stand on Venus, you would feel slightly lighter than on Earth. However, the extreme atmospheric pressure and temperature would make it impossible for humans to survive without protection. Venus' surface appears to be geologically young, with a relatively low number of craters indicating a surface age between 300 million and 600 million years old. Scientists believe that Venus undergoes a cyclical process where heat from the planet's interior causes the surface to be repaved in a global resurfacing event. There is strong evidence of widespread volcanic activity on Venus. Thousands of volcanoes dot its surface, ranging from less than a mile in diameter to over 150 miles or 240 kilometers. The planet has far more volcanoes than any other in our solar system. However, there is currently no definitive evidence that these volcanoes are still active, although recent studies suggest that some may have erupted within the last few million years. Despite the apparent geological activity, Venus doesn't experience significant tectonic activity like Earth. While Venus does have mountain ranges and rift valleys similar to those seen in tectonically active regions on Earth, it lacks the kind of large, distinct tectonic plates seen on our home planet. This might be due to the planet's slow rotation, which limits the Coriolis effect necessary to drive large-scale tectonic activity. Venus' atmosphere is one of its most distinctive and intriguing characteristics. The atmosphere is primarily composed of carbon dioxide, 96.5%, with most of the remainder being nitrogen. However, there are also traces of other gases such as sulfur dioxide, water vapor, carbon monoxide, argon, and helium. This composition is vastly different from Earth's nitrogen-oxygen atmosphere, making Venus air toxic to humans. Venus is arranged in several layers, the troposphere extending from the surface to about 40 miles up, the mesosphere stretching from the top of the troposphere to about 56 miles high, and the thermosphere, which reaches up to 125 miles above the planet's surface. Above this, there's a transitional region called the exosphere that merges with the void of space. The high concentration of carbon dioxide in Venus' atmosphere creates a strong greenhouse effect, trapping heat and making it the hottest planet in the solar system, even hotter than Mercury, which is closer to the Sun. The greenhouse gases in the atmosphere absorb heat energy radiated from the Sun, preventing it from escaping back into space. This results in surface temperatures averaging around 467 degrees Celsius, which is hot enough to melt lead. There's very little temperature variation between day and night, or between the equator and the poles due to the thick atmosphere's efficient heat distribution. This results in a virtually constant, furnace-like temperature all over the planet's surface. The atmospheric pressure on Venus is enormous, approximately 92 times greater than Earth's at sea level. This is equivalent to the pressure experienced 0.62 miles deep in Earth's oceans. A human exposed to such pressure without protection would be crushed. Despite this high pressure up in Venus' atmosphere, approximately 31 miles above the surface, the pressure and temperature conditions are similar to those on Earth's surface. Venus' atmosphere is perpetually cloaked in thick, opaque clouds that cover the entire planet. These clouds reflect about 75% of the sunlight that reaches Venus back into space, which is why Venus is so bright and easily visible from Earth. The winds in Venus' upper atmosphere are incredibly fast, reaching speeds up to 450 miles per hour, much faster than the strongest hurricane winds on Earth. These winds move in a phenomenon known as superrotation, where the atmosphere rotates much faster than the planet's surface. Near the surface, however, winds are much slower, typically less than a few months. Venus boasts the highest mountain in the solar system, Maxwell Mons, rising 20 kilometers, about 12 meters, above Venus's mean surface level. The planet's surface is also marked by numerous impact craters, extensive lava flows, and unique surface features like corona, circular structures caused by the upwelling of hot material from the mantle, and arachnids, circular structures with a complex pattern of fractures. Due to Venus' slow rotation and dense atmosphere, the planet doesn't experience significant seismic activity like Earth. However, recent studies suggest that Venus may still be geologically active. Venus has been a target of interest since the dawn of space exploration. The Soviet Union's Venera and Vega missions, NASA's Pioneer Venus, and the European Space Agency's Venus Express have all contributed significantly to our understanding of the planet. The Venera program achieved many firsts, including the first human-made device to enter the atmosphere of another planet and the first successful landing on another planet. These missions provided valuable data on Venus' atmosphere and surface. More recently, NASA's Magellan orbiter mapped almost the entire surface of Venus using radar to penetrate the thick cloud cover. This mission revealed details about Venus's surface features and geology. Despite the challenges posed by Venus's harsh conditions, scientists are interested in further exploring the planet. NASA's planned Veritas and DAVINCI+ missions aim to study Venus's geologic history and atmospheric conditions, providing insights into whether Venus might have once harbored liquid water or even life. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth took such different evolutionary paths. Japan's Akatsuki mission is currently studying Venus' atmosphere and weather patterns. Venus, our neighboring planet, is an intriguing world of extremes. Its harsh environment poses significant challenges to exploration. Yet, its similarity to Earth in size and composition along with hints of potential past water and geologic activity, keeps our curiosity alive. As we prepare for new missions to Venus, we stand on the brink of major discoveries that could reshape our understanding of the solar system and our place in it. As a reflection on our own planet's potential future, Venus serves as both a warning and an opportunity to exist on Mars or some of the moons of Jupiter and Saturn. For example, more complex life forms, such as intelligent civilizations, could also exist on planets orbiting other stars. The Fermi paradox suggests that if intelligent life is common in the universe, why haven't we detected any evidence of it? Some theories suggest that intelligent civilizations tend to self-destruct, while others propose that they are too far away or have no desire to communicate with us. Ancient aliens. This theory suggests that aliens have visited Earth in the past and have influenced human history and culture. Proponents of this theory point to ancient artwork and texts as evidence of alien visitation. UFO sightings, unidentified flying objects, are often cited as evidence of alien visitation. While many sightings can be explained by natural phenomena or human-made objects, some remain unexplained and could potentially be evidence of extraterrestrial visitation. The simulation theory. This theory proposes that our entire reality is a computer simulation created by an advanced civilization. While not specifically about aliens, this theory suggests that the creators of the simulation could potentially be an extraterrestrial civilization. To start with, let's address the most basic question. Do aliens exist? Well, according to the Drake equation, which was developed in 1961 by astronomer Frank Drake, the probability of intelligent life existing elsewhere in the universe is high. The equation takes into account factors such as the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Using these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. But the question remains, have we ever encountered these civilizations? Many people believe that we have, and there are countless stories of alien sightings, abductions, and encounters. However, there is little concrete evidence to support these claims. So let's explore some of the most popular theories about what aliens might look like. The traditional image of aliens as small, green, big-eyed beings is a product of popular culture. However, it is unlikely that aliens would look anything like this. In fact, it is impossible to predict what aliens might look like, as their appearance would depend on the conditions of the planet they evolved on. For example, if an alien species evolved on a planet with high gravity, they might have shorter, stockier bodies. If they evolved on a planet with a harsh, radiation-filled environment, they might have evolved to be more resilient to radiation. It's also possible that some alien species might not even have bodies as we know them. They might exist as pure energy or as a hive mind collective. But why would aliens visit Earth? There are a few possible reasons. Some scientists speculate that aliens might be interested in our planet because of its unique location in the universe. Earth is in a Goldilocks zone, not too hot, not too cold, and has the right conditions for life to thrive. Aliens might be interested in studying our planet to learn more about how life can survive in these conditions. Another reason aliens might visit Earth is to make contact with us. If there are millions of intelligent civilizations in the galaxy, it's possible that some of them are trying to communicate with us. However, if this is the case, they might be communicating in ways that we can't even comprehend. Their methods of communication might be vastly different from ours. So, what should we do if we ever do encounter aliens? That is a question that scientists and researchers continue to ponder. It is important to approach any potential contact with caution and open minds. Studying and understanding any interactions with extraterrestrial beings could provide us with valuable insights into the nature of our universe and our place within it. Encountering aliens, many scientists believe that we should approach any encounter with caution. We should avoid making any sudden movements or aggressive actions, as these might be misinterpreted by the aliens. Instead, we should attempt to communicate in a peaceful and non-threatening manner. If we do make contact with aliens, it could have profound implications for our understanding of the universe. It could challenge our beliefs about our place in the cosmos and force us to confront some of the big questions about life, the universe, and everything. Now that we've explored some of the theories and possibilities of alien life, let's consider the idea of the Fermi paradox. If there are so many intelligent civilizations out there, why haven't we seen any evidence of them? Why haven't we detected any signals or observed any spacecraft from other worlds? One possibility is that advanced civilizations tend to self-destruct. With technology comes the potential for destruction, whether through environmental damage, war, or some other catastrophe. It's possible that many intelligent civilizations reach a point where they are unable to sustain themselves and ultimately fail. Another possibility is that intelligent civilizations have no desire to make contact with us. Perhaps they are simply not interested in Earth or in communicating with other species. Or perhaps they are too far away to detect our signals and we are too primitive to detect theirs. Regardless of the reasons, the Fermi paradox remains a mystery and a subject of much speculation. But let's turn our attention to the possibility of life in our own solar system. While we haven't found any evidence of intelligent life, there are some promising signs that microbial life might exist on other planets or moons. For example, NASA's Mars rover has detected methane on the planet's surface, which could be a sign of microbial life. And scientists have found evidence of subsurface oceans on some of Jupiter and Saturn's moons, which could potentially support life. If we do find evidence of microbial life in our own solar system, it would be a major discovery and could have significant implications for our understanding of life in the universe. Let's consider the potential implications of discovering intelligent life. If we were to make contact with an alien civilization, it could have profound impacts on our society and our understanding of the universe. For one, it could challenge our existing beliefs and worldviews. We might need to reevaluate our ideas about our place in the cosmos, our religious and philosophical beliefs, and our understanding of the origins of life. It could also raise questions about the ethics of interacting with other intelligent species and the responsibilities that come with such interactions. Another potential impact is on our technology and scientific progress. If we were to encounter a more advanced civilization, we could learn from their technology and knowledge, potentially accelerating our own progress. On the other hand, it could also pose a threat if the aliens have hostile intentions towards us. It's difficult to say for certain whether aliens, if they exist, would be dangerous to us. We have no concrete evidence of intelligent extraterrestrial life, and so any speculation about their intentions or behaviors is purely hypothetical. Some people argue that aliens could be dangerous if they are more technologically advanced than us and have the ability to conquer or destroy us. Others point out that any civilization advanced enough to travel through space would likely have a more sophisticated understanding of the universe and may be more peaceful and cooperative. It's also possible that aliens could be indifferent to us, simply observing us from a distance without any intention to interact with us at all. Overall, while it's fun to speculate about the potential dangers of alien life, the truth is that we simply don't know enough to make any definitive conclusions about their intentions or behaviors. Intentions or behaviors, the search for extraterrestrial life should be approached with an open mind and a healthy dose of curiosity, rather than fear or paranoia. Regardless of the potential impacts, the search for intelligent life continues. We are constantly developing new technology and refining our techniques to search for signals and evidence of other civilizations. And while the chances of finding intelligent life may be slim, the pursuit of knowledge and discovery is a worthy endeavor in and of itself. That's all for today's topic of aliens. We hope you've enjoyed this discussion and learned something new. If you have any questions or comments, please leave them in the comments section below. Thanks for tuning in, and we'll see you next time. Nothing existed at the outset. After that, the cosmos began to take shape some 13.7 billion years ago. How this came to be, or if there was ever a time before time, is still a mystery. Yet, physicists have pieced together an approximate timeline of significant events in the cosmos' existence. Using telescope data and models of particle physics, we can examine key points in the evolution of our universe. If you're interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. The Big Bang. The Big Bang is a moment in time, not a location in space. It is the first second of time, the point in history from which all other seconds have been measured. The Big Bang, despite its common name, was not an explosion, but rather a time when the universe was incredibly hot and dense. before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe was an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing that we don't know for sure what happened at that time. We now understand the cosmos to break down at the Big Bang because mathematical infinities don't make sense in physics equations. Cosmic inflation era. The next cosmic phase was rapid expansion in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. Nevertheless, further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark gluon plasma. The temperature of the early cosmos was between 7 trillion and 10 trillion degrees Fahrenheit, or 4 trillion and 6 trillion degrees Celsius, just a few milliseconds after the Big Bang. Quarks, elementary. Particles ordinarily contained within protons and neutrons were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial state that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances in both terrestrial atom smashers and the early cosmos. The challenging to achieve condition only lasted for a few fractions of a second. The early epic subsequent period of time, beginning perhaps in the neighborhood of a few thousandths of a second following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms, protons and neutrons, fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. Yet this process ceased as the temperature dropped. As temperature settled down 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this epoch, was first identified in 1965. It was created when photons that had previously collided with electrons were able to flow without being disrupted. The Dark Ages refers to a lengthy period of time when nothing in the cosmos emitted any light. The term Dark Ages refers to this time frame of around 100 million years because practically all of what astronomers know about the cosmos can be gleaned by studying starlight. This era remains exceptionally challenging to study, as it's hard to piece together what happened if there are no stars to guide us. The first stars were formed when hydrogen and helium began to compress into massive spheres some 100 to 180 million years after the Big Bang, creating hellish temperatures at their centers. After the neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons generated by early stars and galaxies, the cosmos entered a period known as cosmic dawn or reionization. It's hard to put a time limit on reionization, as it happened soon after the Big Bang, and its signals have been masked by subsequent gas and dust. Thus, the most that scientists can determine is that it was finished by around 500 million years after the Big Bang. Almost a billion years after the Big Bang, supermassive black holes developed at the cores of merging early galaxies. Intense quasars, visible from 12 billion light-years away, switched on and began emitting their bright beams of light. Throughout the subsequent few billion years, the cosmos underwent more evolution. Denser regions in the early cosmos drew more material due to gravity. A gorgeous filamentary cosmic web is the result, slowly expanding into galaxy clusters. The solar system occurred around 4.5 billion years ago, when a yellow star with rings around it formed from a cloud of gas. These accreted rings eventually became the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. Either the third planet out from the Sun retained a lot of water via this process, or it received a deluge of ice and water from comets later on. Earth and humanity. Little primitive bacteria appeared on that third watery world between 3.8 and 3.5 billion years ago. These organisms arose and progressed into amazing marine monsters and enormous dinosaurs that fed on leaves. Some 200,000 years ago, upright beings emerged capable of contemplating the vastness of space and learning about the universe's origin. The end or not? It isn't the final chapter, of course. The future of the cosmos is still a mystery to physicists. It is dependent on our ability to accurately quantify the characteristics of dark energy, the unknown factor thought to be accelerating the expansion of the universe. All the stars and all the galaxies will have burned out, and even black holes will evaporate into nothing. If the universe continues to expand forever, leaving behind a lifeless cosmos saturated with inert energy, this scenario comes to pass. Alternatively, the Great Crunch, a reversal of the Big Bang in which gravity triumphs over dark energy's expansionary force, will occur. The Great Rip, in which the cosmos rips itself apart, is another possibility if dark energy accelerates everything apart to greater and greater distances. Thanks for watching, and don't forget to hit the like button, subscribe, and turn on notifications for more content like this in the future. The universe is a vast and mysterious place filled with countless wonders and secrets waiting to be discovered. Among the many mysteries of the cosmos, one of the most fascinating and profound is the age of the universe itself. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Scientists have spent decades studying the universe using a variety of tools and techniques to unravel the mysteries of our cosmic past. Through their efforts, they have determined that the universe is estimated to be around 13.8 billion years old. The search for the age of the universe began in the early 20th century when astronomers first realized that our universe was expanding. The concept of an expanding universe was first proposed by Belgian astronomer Georges Lemaitre in 1927, but it wasn't until the work of American astronomer Edwin Hubble in the 1920s and 1930s that the idea was widely accepted. Hubble's groundbreaking observations of distant galaxies revealed that they were moving away from us at great speeds, and that the farther away a galaxy was, the faster it was moving. This relationship, known as Hubble's law, suggested that the universe was not static but was instead expanding. If the universe was expanding, then it must have been smaller in the past, and this realization led scientists to wonder just how old the universe was. The first attempts to estimate the age of the universe were based on models of stellar evolution. Scientists knew that stars undergo a predictable sequence of changes as they age, and they thought that by studying the properties of stars in our own galaxy, they could determine the age of the universe. However, these early estimates were plagued by uncertainties in our understanding of stellar evolution, and they varied widely from a few million years to several billion years past. It wasn't until the 1960s that a more accurate method for determining the age of the universe was discovered. In 1964, two astronomers named Arno Penzias and Robert Wilson discovered a faint background radiation that was present in all directions of the sky. This radiation, known as the cosmic microwave background, CMB, is thought to be the leftover radiation from the Big Bang, the event that marked the birth of the universe. The discovery of the CMB was a major breakthrough in our understanding of the universe, and it provided scientists with a powerful tool for estimating the age of the universe. By studying the properties of the CMB, scientists could infer important details about the early universe, such as its temperature and composition. This information, in turn, could be used to estimate the age of the universe. Over the next few decades, scientists refined their measurements of the CMB and improved their understanding of the early universe. They also developed more sophisticated models of cosmic evolution, which took into account the effects of dark matter and dark energy, two mysterious substances that make up the majority of the universe. By combining these observations and models, scientists arrived at an estimate for the age of the universe. This estimate has been confirmed by a variety of independent measurements, including observations of distant supernovae and the large-scale structure of the universe. The age of the universe is one of the most well-established facts in cosmology, and it has profound implications for our understanding of the cosmos. The age of the universe tells us that our universe has a long and fascinating history stretching back billions of years to a time when the universe was just a tiny, hot, and dense singularity. It tells us that the stars and galaxies we see today are the result of billions of years of cosmic evolution, driven by the forces of gravity and the interplay between matter and energy. 13.8 billion years old. Why is it still expanding at an accelerating rate? What is the nature of dark matter and dark energy, and how do they shape the evolution of the universe? How did the first stars and galaxies form? And what was the nature of the universe in its earliest moments? These are just a few of the many questions that cosmologists are working to answer. The age of the universe provides a crucial piece of information in the quest to understand the cosmos, but it is just one piece of a much larger puzzle. One of the most fascinating aspects of the age of the universe is how it connects to the fundamental nature of space and time. According to Einstein's theory of general relativity, space and time are intertwined, forming a four-dimensional fabric known as spacetime. This fabric can be warped and distorted by the presence of matter and energy, leading to phenomena like gravitational waves and black holes. The age of the universe tells us that spacetime has been evolving for billions of years, stretching and warping in response to the forces of the cosmos. It tells us that the very fabric of the universe has a history, and that the structures we see today are the result of an intricate interplay between spacetime, matter, and energy. While the universe is expanding at an accelerating rate today, it is still unclear what the ultimate fate of the universe will be. Some theories suggest that the universe will continue to expand forever, eventually becoming a cold and dark place devoid of stars and galaxies. Other theories suggest that the universe will eventually collapse in on itself, leading to another Big Bang and the birth of a new universe. Whatever the ultimate fate of the universe may be, the age of the universe tells us that we are living in a remarkable moment in cosmic history. We have the opportunity to study the universe at a time when it is still evolving and changing, when stars are still being born and galaxies are still colliding and merging. By studying the universe and its evolution, we can gain insights into the fundamental nature of the cosmos and our place within it. The age of the universe also provides us with insights into the vastness and complexity of the cosmos, sparking our curiosity and driving our exploration and understanding of the universe. Into the likelihood of intelligent civilizations existing elsewhere in the cosmos, if life is a relatively common occurrence in the universe, and if the conditions for the development of intelligent life are present on other planets, then there may be many civilizations out there that are much older and more advanced than our own. Moreover, the age of the universe has implications for our search for extraterrestrial life. By studying the conditions that led to the emergence of life on Earth, and by exploring the diversity of life forms on our planet, we can gain insights into the types of environment and conditions that might be conducive to the emergence of life elsewhere in the universe. Some theories suggest that the universe is just one of many in a multiverse, a vast and complex network of parallel universes with their own unique properties and histories. The age of the universe tells us that if a multiverse does exist, then there has been ample time for the emergence of many different universes, each with its own unique history and destiny. Finally, the age of the universe reminds us of the incredible beauty and wonder of the cosmos. From the cosmic microwave background radiation left over from the Big Bang to the intricate dance of stars and galaxies across the night sky, the universe is a rich and complex tapestry of phenomena that is both awe-inspiring and humbling. In conclusion, the age of the universe is a remarkable fact that has profound implications for our understanding of the cosmos and our place within it. It tells us about the origins and evolution of the universe, the potential for extraterrestrial life, the nature of reality itself, and the beauty and wonder of the cosmos. As we continue to explore the mysteries of the universe, the age of the universe will remain a key piece of information guiding us in our quest to understand the planets that circled around our sun. But now we know that there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very, very violent. Planets are made the same way everywhere. They come from the dust and other things that are left over after stars are born. So if they're all made the same way, what makes them so different? They have found more than 400 planets. Some are huge spinning balls of gas that are 5 times as big as Jupiter. Others are huge rocky worlds many times larger than Earth. Some follow wild erratic orbits, so close to a star they're burning up. One thing is clear, no two planets are the same, each one is unique. But most of these new worlds are very far away and hard to study. Most of what we know about how planets work comes from the 8 that circle our Sun. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. And in the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, they started to develop their own personalities. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal planets closer to the sun and the gas planets farther away, came from this cloud of space debris. All of the worlds in our solar system are made of the same materials. They're made from the same cloud of gas and dust, but they formed under very different conditions. Some of them formed close to the sun where it was much hotter, and some formed far away where it was much colder. And since the situations were so different, the things that came out of them were also different. So at the beginning of the solar system, there was a pretty even mix of silicates, water vapor, hydrogen, methane, and others. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the ingredients are mixed and how hot the oven is. And you mix the ingredients just like you did with the cake, then you put it in the oven and bake it, and it would change. So basically, this is what happened in the solar system overall. The planet cooks in a slightly different way depending on how close it is to the sun. Near the sun where it is hot, gases are burned off and water boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants and none. As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our sun system, but now we know that they are just a small part of the huge family of planets in the sky. It's a very important moment in the history of science to be sure that there are other systems of planets out there. And in our Milky Way galaxy, which has 200 billion stars, there are probably dozens of planets. NASA sent the Kepler Space Telescope out into space in 2009 on a 6-year mission to find new planets that orbit other stars. At all, if you want planets that are made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to condense out as solids. And these very small mineral grains can start to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, they would basically hit each other and make one slightly bigger dust molecule. And they keep getting more and more. As these things got bigger, this process they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things towards it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were a lot of young planets in our own solar system, maybe 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid for Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a sphere shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across. Then it has enough gravity to crush it into a sphere. Any smaller and it stays in an irregular shape. Every time a round baby planet crashes into something, it makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things like most metals fall down and form a much denser core at the planet's center. Finally, the young planets are starting to look like planets. But now they have to make it through a time of violence and destruction, a cruel time that will decide which planets will live and which will die. After the sun was made, all 8 of our planets came from the same cloud of dust and gas, but they turned out to be very different. There was no real plan for how each of the new planets should be made. They did follow the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our sun was surrounded by about 100 young planets. It turned into a demolition derby. Planets hit planets. Most were wiped out. The early history of these planets would have been very, very violent, with many of these collisions happening in the last stages of each planet's growth. As these collisions happened and things ran into each other, some of the planetesimals started to grow at the expense of the others. And these things that would eventually become planets grew and grew. As they got bigger, they sucked up all the smaller planetesimals around them, which caused a lot of space debris to hit the surface of the protoplanet. After it was over, there were only 4 different rocky planets left. Because of the things that happened to each planet in the past, they are all so different from each other. Mars is a frozen wasteland. Earth flows with liquid water. Venus is a place full of volcanoes, and Mercury is small, empty, and very hot. Because of a huge crash, Mercury, for example, has a very thin crust and is very dense. So it could have been a bigger planet in the past. Then something hit it at an angle, which tore off the lighter crust and left only the dense center. Also hit hard was the young Earth. At the end of the Earth's development, it was hit by something else, which tore apart its mantle and sent the pieces into orbit around the Earth, where they regathered to form the Moon. Something also seems to have crashed into Mars. The crust of the Earth is thinner in the north than in the south. One idea about what might have caused this is that the northern hemisphere of Mars was hit by something early in the planet's history, which blew off a lot of its crust, and that crust started to build up again in the south of Mars. There were 2 effects of all these collisions. They cut down on the number of baby planets that were still alive, and they brought more ingredients to the survivors. If you had a collision with something that was metallic, those chunks would tend to descend down into what was becoming the core. Where if you collided with something light or icy, they would tend to just float about and form part of the crust instead. Near the sun, there were 4 rocky planets that were almost done. They were made of a solid core of hot iron surrounded by a layer of liquid iron and a shell of molten rock. On top of that is a crust on the surface. All of these rocky planets were made the same way from the same basic materials, but each of them was very different. Space may look empty, but it's not. It's full of stuff blown out of the sun. Strong magnetic fields are made by the sun. These fields rise up in giant loops above the surface. When they hit each other, a storm of very hot, very charged particles shoots out into space. The name for it is the solar wind. Astronauts can see it from space, but only when they close their eyes. When you close your eyes, you sometimes see a little flash, and that flash of light is caused by an energetic particle going through your head and interacting with the fluid in your eye. Solar wind could kill the astronauts if they were exposed to a lot more of it. During the Apollo program, there was an explosion on the sun between 2 moon missions that would have killed the astronauts if they were there. So radiation in space is a big deal. But here on Earth, the solar wind doesn't pose much of a threat because we are protected by an invisible magnetic field that comes from the center of the Earth. You can make magnetic fields from motion by converting the energy of the motion into magnetic energy deep inside. The Earth. The same thing happens as the Earth spins. The hot liquid metal flows around the solid core, turning its energy into a magnetic field that comes out of the poles. It keeps the solar wind from getting into the atmosphere of the planet. And if the planet has a magnetic field, the magnetic field will send the solar wind around the planet. The solar wind is pushed away from Earth by the magnetic field, which protects the atmosphere and everything on the surface. Big storms of solar radiation can sometimes mix up the magnetic field. Then big light shows called auroras happen over the poles. Without a magnetic force field, Earth's atmosphere and water would be blown away by the solar wind, leaving a planet that is dead and dry, a lot like Mars. Mars was made the same way Earth was, but today it's cold and dry, and there's not much going on. So why have the two planets changed so much? NASA sent two robots to Mars in 2004 to find out what was there. The Spirit and Opportunity rovers looked at miles of the surface of Mars. They proved that Mars is a dry, dangerous desert with only a thin atmosphere. But they did find signs that water used to be there. Mars wasn't always a dry, barren place. We have found strong evidence that water was once below the surface, rose to the surface, and evaporated away. In a few places, we can also see ripples that are made when water flows over sand. So not only was there water underground, it had flowed across the surface. If Mars used to have water, it probably also had a lot of atmosphere around it. So what happened? We can see that there were volcanoes on Mars in the past, so it had a hot interior at some point. And because it was made of the same stuff as Earth, it would have had a hot iron core surrounded by liquid metal in the middle. It should have also had a magnetic field. The question is, where did it go? Early in the planet's history, Mars apparently had a strong magnetic field, and it was probably caused in the same way as it is on Earth. But Mars is a smaller planet than Earth. Because of this, it will lose heat more quickly, and that means that a liquid core can become solid when it freezes. If you completely freeze the core, the convection will stop, the flow stops, and the magnetic field disappears. As soon as the magnetic shield stopped working, the solar wind blew away the atmosphere, and the water evaporated. Mars turned into a cold, empty place. The rocky planets Mars, Earth, Venus, and Mercury all formed within 150 million miles of the Sun. But 4 times farther out, the Sun baked a very different kind of planet. These monsters are very big, made of gas, and have no solid surfaces at all. So far, astronomers have found more than 400 new planets in solar systems far away. Almost every one of them is huge and made of gas. Our solar system has 4 of these gas giants: Jupiter, Saturn, Uranus, and Neptune, all of which have thick, soupy atmospheres with lots of hydrogen, helium, and methane. Why are these outer 4 made of gas when the inner ones are rocky? It's very cold here, 500 million miles from the Sun. At the start of the solar system, there was some dust but mostly gas and water frozen in ice grains. It was cold enough to make solid snow where the big planets began to form. And we think that we were able to make ice snowflakes, and that these were able to stick together to form the cores of the giant planets. We think that's why the big planets might have grown so big, because there was so much ice and gas. Their cores grew to be about 10 times the size of Earth. A lot of gravity came from these big cores. They had so much pull that they sucked in all the gas around them and made thick, soupy atmospheres that went down tens of thousands of miles.
More and more dust
The
and
more
debris
gravity
kept
kept
getting
getting pulled towards the planets, and this is what made up their moons. Each of Jupiter and Saturn has more than 60 moons. The gas planets have something else that makes them unique rings. Saturn is different from the other planets because it has these beautiful rings. It turns out that Jupiter, Uranus, and Neptune also have rings, but they are very weak and hard to find, but they are there. There are rings around all 4 of the gas giants, but Saturn's are the most obvious from far away. Saturn's rings look like a single flat disk, but in reality they are made up of thousands of small rings that are only a few miles wide each. When the Cassini probe flew by, it found that billions of pieces of ice and space debris were moving around inside the rings at up to 50,000 miles per hour. These pieces of ice and rock hit each other all the time. Some of them turn into small moons, some of them fall apart. But they never grow bigger because Saturn's huge gravity pulls them apart. Scientists are just now starting to figure out how the rings came to be. The idea is that a comet hit a moon and knocked it out of its orbit, bringing it closer to the planet. Saturn's gravity tore it to pieces. All of that stuff got stuck in rings that went around the planet. But the real mysteries of the gas giants are deep inside them, tens of thousands of miles below the clouds. Here is where things really get going. It's a place so extreme that it goes against the natural laws. Most of the new planets we find orbiting faraway stars are huge gas planets. They are so big that Jupiter seems small next to them. But nobody knows what happens inside gas giant planets, whether they are in our solar system or far away. We know that Jupiter's thick atmosphere goes down 40,000 miles, and we can see bands of gas moving at high speeds that make violent storms on its surface. But we don't know what's happening inside far below the storms. NASA sent the Galileo spacecraft on a 14-year trip to Jupiter to find out. December 7, 1995, Galileo sent a probe into Jupiter's atmosphere, which it did at a speed of 160,000 miles per hour. As it fell through the thick air, the parachute slowed it down. It saw lightning in the clouds and 450 meters per hour winds. The probe transmitted data back to Earth. For 58 minutes, what happened to the Galileo probe that we dropped, and it didn't hit anything. It just kept falling into Jupiter's environment, and the pressure kept going up and up and up. As it fell, it measured pressures 23 times higher than on Earth and temperatures over 300 degrees higher than on Earth. When you're in the environment of a gas giant and you go deeper and deeper into the soup of hydrogen, which has no solid surface, it can still be very heavy, and so eventually you would be crushed by the overlying weight of the material that's there. Even though the probe only went 124 mil down before it was crushed, it showed scientists what Jupiter's inside looked like, but the dark heart of the planet still remains a mystery. Like some rocky planets, the gas giants have a magnetic field too. Jupiter's magnetic field is 20,000 times stronger than Earth's, and so big that it goes all the way to Saturn, which is more than 400 million miles away. Like on Earth, Jupiter's magnetic field keeps the solar wind away from the atmosphere and keeps it safe. When scientists looked at Jupiter's magnetic field, they found that it affected the moons of Jupiter. The volcanic moon Io orbits only 217,000 miles from the planet. Every second, Io's volcanoes send a ton of gas and dust into space. It gets even stronger because of Jupiter's magnetic field, which makes powerful belts of radiation. And this makes the area around Jupiter very busy in a lot of ways. If you point a radio antenna at Jupiter, you can hear how the planets and the magnetic field interact with each other. Jupiter and Saturn can make auroras without the solar wind. They make their own magnetic fields because they're so big. These auroras show that planets with gas also have magnetic fields. But how do magnetic fields get made on gas planets on Earth? The job is done by a very hot liquid metal that spins around the planet's solid iron core. Most likely gas planets do about the same thing, but gas planets don't have iron cores. They get very hot. They formed around frozen cores of dust and ice, so we don't really know what's going on inside. We really don't know what makes up the deepest parts of Jupiter's interior, so it's possible that Jupiter has a solid core at its center, or no probe could ever go the 44,000 miles to the center of the planet to look into it. Galileo was destroyed before it could reach the center of the planet. Gravity and heat shape how planets evolve from their inner cores to their outer atmospheres. They're the great creative forces in planet building. But there's one more thing that has a big effect on how planets turn out, and that ingredient is water. Planets may look like they are fixed and don't change, but they are always changing. One planet in our solar system lost its atmosphere and turned into a desert. Another planet got too hot and changed into the planet from hell. Planet Earth has also changed. And it was water that changed the game. When you look at Earth from space, you can see a lot of water. We are, after all, a blue planet. That means it must be very wet. Right at first glance, our world seems to have a lot of water. After all, 3/4 of it is made up of oceans. Not true. Only 0.006% of the mass of the Earth is water. Some water is on the surface as oceans, and some is stuck in the mantle. But actually, the Earth is a relatively dry rock. All of the inner rocky planets form very close to the sun, so they started off dry. Any water they might have had either evaporated or was blown away. When things hit, these massive collisions that formed the Earth were so energetic that if there had been water here, it would have evaporated and left the Earth. So where did all the new water on Earth come from? It's now here. When you look at Jupiter, Saturn, Uranus, and Neptune, you can see that they have a lot of water lock up inside them, and even more dramatically are the moons. At least half of the water on the moons of Jupiter, Saturn, Uranus, and Neptune, a lot of water was out there. So how did some of it get to planet Earth? And the answer is almost certainly that there were some asteroids and comets left in our solar system that were far enough from the sun that they could keep their water. There were millions of these watery asteroids and comets that flew into the inner solar system. Some of them crashed into our planet. Over time, the Earth got the water that used to be in the asteroids. This is what makes up the mass of water that now covers almost all of the Earth. Without surface water, there would have been no life. What about water that is too much? The oceans would be much deeper and cover the continents and even Mount Everest, and it's likely that the exact amount of water that the Earth has is what made it possible for us Homo sapiens to evolve into a technological species about 4 billion years ago. A blizzard of comets and asteroids brought just the right amount of water to Earth. This is how the world we know today came to be, and it's possible that the same thing is going on somewhere else in the universe. Right now, there is a lot of water out there. That much is certain. The most common atom in the universe is hydrogen, and oxygen is one of the next most common. H2O will definitely be a very popular molecule, which is exactly what is happening in our universe. So water is everywhere in the universe, and we're finding that planets are too. But we haven't yet found another planet where water is liquid. More than 400 new planets have been found by scientists. Our world doesn't look like any of them. What we haven't found yet is a planet around another star that is about the same size, mass, and chemical makeup as Earth, so it remains an extraordinary holy grail for humanity to find other abodes that remind us of home. But we'll keep looking. We know that our galaxy alone has around 200 billion stars, and up to 40 billion of them could have their own planets. We are entering what will be called the golden age of planetary exploration. In the future, we'll start to really understand for the first time how different things are out there. I think this is going to be a very exciting time. The laws of physics and chemistry tell us how planets are made. Many scientists think it's only a matter of time before we find another planet like Earth, one that formed from the same materials in the right place with the right amount of water. One thing is certain: there are billions of planets out there waiting to be discovered.